Now we will come back to randomization. That is one of the uh, important important tools in this experiment design. So remind that all these blocking factors and and yeah, blocking and factors are very important to identify different sources of variability, but we are sure that we have left out many other possible factors that for some reason we didn't think of them, but they may affect our measurements. And the best way to address them is by randomizing. So once we have homogeneous blocks, then we randomize and assign each one of the individuals to one of the treatments at random. And here you have an explanation why this randomization is important. So let's say that you have 8 students and they are divided in 2 groups. Each student has the same probability of being any of the 2 groups. And the first 4 students receive a special training program, while the second group receives the standard training. Now you have the scores, and so these are the scores of the people in one of the groups, and these are the scores in an exam for the second group. So what is the probability that the 4 students in group 1 are at the top of the list? And you may calculate this p-value. It is 1 over 70, and this is smaller than 0.05, and then you would reject the null hypothesis that both groups are equally perform equally. So because you randomized at the beginning the students, these results are generalizable can be generalized to the whole population. Let's consider a different situation. We give a test to 8 students, and then the scores are these ones, and then we look at which are the characteristics that make up this group. So what are the features of this group that this other group does not have? And maybe what you find, so you measure many characteristics, and maybe what you find is that these 4 people are older, so maybe being born earlier in the year, so they are about 6 months older than the other people in the same course, and then these 6 months make a difference. Could be maybe they are blonde people, so being blonde for some reason make you smarter, or maybe they are the people born from Aries to Virgo. So if you measure many characteristics, it is likely that you will find one of the characteristics that is different between the 2 groups. It may be true. It may be being born from Aries to Virgo makes you especially good in statistics, maybe, but then you have to confirm that. So what is bad is that you discover something kind of by chance, and then you stop there. So if that is now your hypothesis that being born from Aries to Virgo is make you smarter in statistics, now you have to confirm. So now you will give a new exam, and now you will pay attention to this variable and how the distribution of grades between this group and the other group behaves in the next experiment. But you cannot stop after making a postdoc observation like this one. That is why these case studies experiments are not experiments, because they are observations. In medicine, they have very bad fame. Okay, how to randomize? If you know all the units at the beginning, then it is very easy. So you can simply perform a random permutation of all the units, and it is important that this randomization is done by a computer, because people humans tend to create patterns when they randomize. There have been some very interesting studies about this. And if units arrive sequentially, you may not assign randomly so easily. So this is a very easy way of making both groups to be more or less equally balanced until the end, and at the end you're sure that they will be absolutely balanced. So the idea is that you assign to group 1 with probability P1, and this P1 makes use of what is the total size. This is the total size divided by 2, and G1 and G2 are the current sizes of groups 1 and group 2. So for instance, let's say that we are starting our experiment. So at this beginning, group 1 and group 2 will have 0. So you will be assigned to P1 with probability 4/8, that is 50%. And now let's say that just by chance the group 1 is filled. So we have already reached 4 people in the group 1. So then we see that P1, when the 5th person appears, he will be assigned to group 1 with probability 4 minus 4, so that is 0. So and then divided by whatever, so it is 0. So it will not be assigned to group 1. So at the end of the experiment, you are sure that both groups will have the same size. So this is a very clever way of randomizing when these units arrive sequentially. And we may also make this randomization by blocks, or considering blocks. So let's say that units arrive sequentially, and then there are a number of variables that you think that may affect your results. So for instance, you think that the age, we have 4 groups of age, and then sex, and then occupation. They may all affect our results. So at the beginning of the experiment, let's say that we have 2 treatments. So at the beginning of the experiment, they will be assigned to treatment. The first person will be assigned to treatment A or B with probability 0.5. Let's say that we are in the middle of the experiment, and these are the group sizes for each one of the treatment. So we have for treatment A people smaller, younger than 30 years old. We have 10 A's and 6 B's, and then between 30 and 50 we have 12 and 12, and so on. So some of the groups are more imbalanced than the others. Okay, so now a new person appears in the study, and this person is a male with 28 years old, an occupation of type 4. Okay, so we look at so initially it would be assigned to treatment A with probability 0.5, this one, but then we look at the current composition of the groups. So he's younger than 30 years old, so if we put it randomly in A and B, we may create a higher imbalance. On the other side, we don't want to put him straight on group B. We have to look at the remaining of the groups. So a clever way to try to balance, is to multiply this 0.5 by the ratio between the group sizes between A and B. So B is smaller than A, so this ratio will be smaller, so the total probability of finishing in A will be smaller. And the same, this male, so male again, group A is more unbalanced, so we multiply also by a number that is smaller than 1. And then in occupation 4, again it is a little bit unbalanced, so again we multiply by a number that is smaller than 1. So the probability of being assigned to 1, if you multiply all these, is 0.19. So now you you take a random number between 0 and 1, and if it is smaller than 0.19, it will go to group A. But chances are that with 81% of probability it will be in group B. So you try to compensate this imbalance between the sizes, the current sizes of groups A and B. And remember always that blinding is also important. So it is randomization and blinding. So when we want to account or to address or to be protected against sources of variability that have not been blocked or designed specifically designed in the experiment as a factor or as a block, then the main two tools are randomization and blinding. We can do single blind, in which the patient is blinded. We can do double blinded, in which the doctor is also blind, because otherwise the doctor may somehow bias the way the information is given to the patient, or the way that the treatment is applied. And the reason is that these doctors and patients tend to evaluate differently if they know that they have been given treatment 1 instead of treatment 2. And doctors, so when the doctor is blind, the doctor should not be able to distinguish which patient is receiving which treatment, because otherwise he will inadvertently behave differently. And for a small number of treatments, blocks should contain more than one replicate for each treatment, because otherwise we don't have enough power. So this would be all for the randomization and for the lecture.